Okay, YouTube, in our last video, we explored how to add and subtract rational expressions already having common or like denominators. In this video, we're going to focus on how to add two rational expressions, especially those containing variable expressions, when you don't have a common denominator. And so we're going to look at actually two different methods for doing this. And I hate to say, but for the most part, it's going to be personal preference. But I definitely prefer one of the ways over the other, and I'll share that with you here. But I want to look at two different ways to add together rational expressions not having common denominators. So we're going to start by taking a look at what this would mean. And in terms of what we mean, we say that letting A, B, C, and D be expressions excuse me, where C and D are not equal to 0, because what we are doing here, we are either adding together or subtracting apart A over C and B over D. So of course, we wouldn't want to have C and D be equal to 0 here, but in either instance, this is my favorite part about using these methods up here. It says that if you want to find a common denominator between this expression C and this expression D, it says that your common denominator is always just CD. And the reason why is because, well, I don't know, let's face it, if we had something like, I suppose 1/3 plus 4/5, something like this, then we could say that our common denominator quite simply would just be the product of 3 times 5, because if we were to take everything over here times 5, and if we were to take everything over here times 3, then we would guarantee to have a common denominator that would be the product of these two things. And so what you're seeing for the rest of this pattern here, besides the CD part where we have the product of these two is the common denominator down here, then on top what we get is this: since we have to take everything over here times, a D on top and bottom, and everything over here times a C on top and bottom, what we get is really A times this one's denominator plus B times this one's denominator. So in a quick sense, I suppose what you're going to see is this. Up here we would say that, excuse me, 1/3 plus 4/5 has a common denominator of 3 times 5, and then we would just get 1 times 5 in the top left corner, plus now 4 times 3 in the top right corner. And so what we end up with is this 17/15. So that's just a pretty slick method. I do like this a lot. So we're going to look at using this method to find addition and subtraction, I guess sums and differences. Now the second method, and we'll go back to the first method, we'll use both here on this example, so don't think that I think you've got it right now. We'll take a look at it again. But the second method, it's actually going to involve what we call the LCM. And the LCM is the least common multiple. And the reason why we explore the LCM is because, well, the example I used up there was 1/3 plus 1/5. Let's say that I had 1/3 plus 1/9. According to our method above, then we would see that, I suppose, that our common denominator here would just be 3 times 9, and what we would get is 1 times 9 plus 3 times 1, or 1 times 3. So really we get 9 plus 3 on top all over 12, which comes out to be 27. It's not over 12. 27. So we get 12, 27. So this would be a pretty slick method, but what I want you to see here is that 12 and 27 share a common factor of, well, you guessed it, 3. So if we were to reduce this by a factor of 3, we would get a 4 on top, and 3 times 9 is a 27, we get 4/9. So we get a 4/9 here. Now the beauty of using the least common multiple, and looking at this example again, the least common multiple would have just been 9 between both of these. It would have been that we could have just called this 3/9 plus 1 more ninth, and then been done by calling this the 4/9 that it is. So the neat thing about using the LCM is that it takes the reducing that you have to do after the addition or after the subtraction, and it does it first, or at least it avoids it altogether. So to find the LCM of two or more expressions, here's the rules. We're going to factor the expressions completely. We have to know every factor in the product, and we're going to say that the least common multiple is the product, so this means multiplication. The product, let's try that again, multiplication of the highest power of each factor that appears in any of the expressions. So before we take a look at adding these two rational expressions together, we're going to take a look at just this example where we have this algebraic expression and this algebraic expression, and what we're interested in doing is finding the LCM. So very quickly here, let's go ahead and take a look at both of these, factoring them first. So I notice that these have a common factor of 4, and also I notice that once I factor that out, I'm left with the difference of squares here, so I get an x plus 2, x minus 2, a set of conjugate pairs here. Excuse me. So this is our completely factored form of this initial expression. Taking a look at this next expression, 6x squared minus 24, x plus 24. We see that this has a common factor. They all share a common factor of 6, and factoring that out, This would give us x squared minus 4x plus 4 left on the inside. And again, this thing here is factorable. So we say 6 out in front. What are two factors of a positive 4 that add up to be a negative 4? Well, this had to be a negative 2 and a negative 2. Okay, so this is the cool bit about this. And you know what? Actually, I want to take this a step further just to show you something here. That 4 is really 2 times 2. So I'm going to say 2 squared times x plus 2, x minus 2. And over here, we're going to say that this 6, this is really the same thing as 2 to the first times 3 to the first times x minus 2 times x plus 2. Sorry, minus 2 minus 2. I just want you to see that we would want to get this down into its most essential prime factors. And so from there, we could see that going through factor by factor here, we can find the LCM. So the way the LCM works is, again, let's read this critically here. It is the product, or what we get when we multiply all of the highest powers of each factor that showed up in both of these expressions. So I suppose what we mean here is this. Looking at all of your factors, I say start on the left here. I suppose we could start there. I have a factor of 2, and I have the highest power of 2 is 2 squared. And as I look over here, I say this is 2 to the first. So of my 2 to the second and 2 to the first, the one that has the highest power is 2 to the second power. So we're going to put that on our list here for our LCM. Now moving to our next factor in our first expression, we see x plus 2 to the first. Over in this expression here, we have not even a single x plus 2. So we would say that x plus 2 to the first is the highest power of that factor there. So we would say x plus 2 to the first. Now going on to our x minus 2 here, we see that x minus 2 happens one time over here, but happens twice over here. So our highest power of x minus 2 is squared. And then looking over here, it looks like we've accounted for our 2's, our x minus 2 and our x minus 2. The only thing we haven't confronted yet is this one had a 3, this one had no 3's. So 3 to the first and 3 to the 0 here, looks like between those 3 to the first makes the list. So to clean this up a little bit here, we'd say 2 squared, which is 4 times 3. We get 4 times 3 times x plus 2 to the first, x minus 2 to the second. Or in other words, we could say 12 x plus 2, x minus 2 to the second. This wouldn't just be a common denominator between these two expressions if they were denominators. This would be the least common denominator because these are the least common, or this is the least common multiple of those two expressions. So knowing this, we're going to take a look at the two ways of adding together two fractions here, starting with the most general way of just saying that the least common, or not the least common denominator, but the common denominator between these two things would just be the product of these two denominators here, c times d. So to work with this, the way this works is our final sum here, we're going to take a look over here, is AD plus BC all over CD. In other words, the common denominator is going to be the product of these two denominators here. So we just get the product of these two things. And the way the top works is this 7 right here, we would have had to have taken it times the 3x squared plus 3x, since what we're doing on the left here is taking 3x squared plus 3x and multiplying it by the top and the bottom. So now we'd say plus plus b times c. So we're going to take what's up in this numerator times everybody in this denominator down here. Let's see if I can get some of this stuff out of here. Sorry. If we take now plus x times 9x squared, this right here is, as a matter of fact, this is the combined sum. So the only thing we have to do now is simplify and simplify basically. So looking at the top here, let's go ahead and rewrite it. We multiply the 7 through, we get 21x squared plus 21x's. Now this is plus 9x cubed from this over here, and this is still all over 9x squared, 3x squared plus 3x. And so as we work with this here, we would say that we want to put the top in order here, at least in standard form, where our exponents are in decreasing order. And then what we're going to do is factor and simplify. So this is still all over 9x squared times 3x squared plus 3x. But in terms of factoring the top and the bottom, what do we notice is a common factor at the top? So I notice that they all share a common factor of a 3 and an x. So looking at the top again and reassessing what would be in here, we would be left with a 3x squared plus a 7x to the first plus 7, which I don't think factors anymore. And on the bottom here, 9x squared is just 9x squared. That's fine. But I noticed that 3x squared and 3x have a common factor of 3x. So I'm going to take that 3x out in front and write what's left here, which is x plus 1. So the way this works is we cancel out any common factors, which appear in this case to be just the 3x. Excuse me. So what we get left with on top is 3x squared plus 7x plus 7. And this is all over 9x squared times x plus 1. So this right here, one thing that we want to make sure we do is restrict the domain if necessary. And I notice that in the denominator here, 9x squared equals 0 if x equals 0. So we better not allow x to equal 0. And I notice that x plus 1 equals 0 if x equals negative 1. So we're going to restrict those from the domain. So with respect to this method, I think this is really quick because you could just say that the common denominator is just the product of these two things and write it that way. And then we'll just take everything in the first numerator times the second one's denominator and add that or subtract that to everything in the second one's denominator times the second one's numerator times the first one's denominator here. And then we'll just add these up, simplify, factor, and then cancel out anything they have in common. So now the second method, this is method 2. So method 2, which is the LCM. The way this works is this. The first thing we do is look at the two expressions that we have here and we factor the denominators. So we have 7 over 9x squared plus x over, and what I'm going to do is I'm going to factor out both denominators completely. Once we get these two factored, okay, what we're going to do is find the LCM between these two expressions. So the LCM, we want to start by listing this here. We're just going to go through and say what's the highest power of each factor in the product. So our 9 here, one thing I want to point out here is that this 9 is really 3 squared x squared. But looking at both denominators, we have a 3 to the second here and a 3 to the first here. So 3 to the second makes the list. Now, looking at this first denominator again, we have an x to the second power and an x to the first power over here. So the highest power of x is 2. And looking at the right denominator, this had an x plus 1 to the first. This doesn't have an x plus 1. So the highest power of x plus 1 is just 1. So our least common multiple is 9x squared x plus 1. Now I'm going to put a big box around this because here's what we're going to do. We're going to take our initial expression up here and we are going to modify both of these expressions on the right and the left. I'm going to leave this factored here. And the way we're going to do this is we're going to multiply the top and the bottom times what we need to in order to make each of these have this LCM. So we want these to have the LCM. So as we look at this here, what we're saying is really in the first denominator I already have the 9 and the x squared. What else would I need? Well, I would need x plus 1 on top and bottom. So we're going to multiply the top and the bottom times x plus 1 on the left fraction. And on the right, I guess, expression here, we need a 9x squared x plus 1. Well, we already have the x plus 1. I already have that. We have an x to the first and a 3, but what we're going to need is a 9x squared. So we're going to have to take it times another 3 and another x. And what you do to the bottom there, what we multiply the bottom by, we have to multiply the top by. So what we end up with is really this. We have 9x squared x plus 1. And on top we get 7 times x plus 1. And this is all now times, or sorry, being added to. Over here we get a 9x squared x plus 1 in the denominator. But on top we get x times 3x, which is 3x squared. So the way this works is now we have the smallest possible common denominator, or least possible common denominator. And on top what we get here is, I suppose if I'm writing this in standard form, I'll do that on the next line here, 7x plus 7 plus 3x squared. We end up with 3x squared plus 7x plus 7. And this is all over 9x squared times x plus 1. So what I want you to see is that both of these expressions here are the exact same expression. It's just that the tact that we take is a little bit different. So it's going to be personal preference, but I would say that certainly the best way to do it, my preference, is using the LCM, because what that does is it takes out the simplifying you have to do at the end by factoring the top and the bottom and canceling out common factors. So you tend to stay with smaller values. So we'll look at another example in the next video on how to do this with unlike denominators. Cheers.